Hopefully we'll find out now. Okay, so the aim of what I'm going to talk about here is to explain using actual data. So there's an awful lot of opinion out on the internet, and we have the same opinions on our own website, but as far as I can tell, there's not a lot of data actually backing up a lot of the claims that are made. So I want to use actual data to show how the thermal mass of the insulation materials that we're using inside buildings actually does affect the internal environment. And also, when it comes to thermal mass, there is the general assumption that high thermal mass is good and low thermal mass is bad, which again is not strictly true. It does depend on how buildings are used and how occupants live in buildings. So yeah, hopefully that's what I can talk about. That's what I can show. So firstly, thermal mass. What is thermal mass? It's a bit of a colloquialism because it's not really a technical term as such, but when we talk about it, we're usually referring to the amount of heat that a material stores. Now, the materials that store the most tend to be materials with very higher density, but also high specific heat capacity. So those two properties combined allow a material to store quite a lot of heat. The properties that I'm going to be talking about are not hidden properties. They're all widely available properties that you can just pick up a data sheet and look at, and you can do all these calculations yourself. So there's nothing here that should be terribly surprising. I am going to be a bit table heavy and graph heavy, so do feel free, if you are interested, to download the presentation and sort of look at it and look through it at your own pace. But using thermal conductivity, specific heat capacity and density, we can calculate properties that you don't commonly look at, really. Some of the properties that I talk about are actually mostly used in things like electronics, actually, and Mark's a big proponent of the way that the food industry looks at water activity instead of relative humidity. So just really different ways of looking at product. And the other thing about thermal comfort as well, it's obviously keeping the internal environment at a nice, comfortable temperature, but it isn't just about winter temperatures, it's also about summer. And actually, the way that the climate is changing, the enormous heat waves that we seem to be getting these days are really critical to consider. So yes, in older buildings, the drive is more to sort of stay warm, but actually once you start insulating a building, you've also got to think about how you keep it cool as well. Okay, the properties that I was going to talk about are, the first one is thermal diffusivity. Now, that's a term used to describe how quickly heat moves through a material, and actually it's the way temperature changes propagate through it technically. But you use those three properties that just the specific heat capacity and density and thermal conductivity to create that term. The other term that I'll look at as well is effusivity, which is sort of the reverse of diffusivity, but it describes how a material can transfer heat from itself back to another material when they come into contact. That can be fluids. It doesn't have to be like air. It doesn't have to be another solid. But actually, our hands are really good at detecting how the sort of effusivity levels of materials. We've got a lot of thermoreceptors in our hands, and they're incredibly sensitive. So your hand's actually a great way to to feel how well materials do that. Anyway, waffling. We combine those two terms along with heat storage, and then hopefully I can explain how the thermal mass of those materials can affect the internal environment and also the comfort levels. Okay, I'm going to do my mouse now. Come on, there we go. Can you see the dot? I'm hoping you can see the dot. So when we're looking at insulations, this column, thermal conductivity, is the main one. You've got typical U values of fibrous materials are sort of in the 0.3s, the upper 0.3s for wood fibre, sheep's wool in the middle there, straw around about 0.6, cellulosic materials tend to get down to about 0.038. Then you go on to the synthetic materials, and they do come down a bit. You've got 032 for fiberglass, 035 for mineral wool. PIR is a bit of an outlier at 022, which is why people tend to err towards it. And these are I appreciate you can go lower with PIR, but when you're using internal wall insulation, you would generally try and avoid the foil-faced board. So the actual unfaced PIR tends to be around about 0.022. EPS and XPS are, again, similar sort of values. So, in general, you're looking at sort of similar range. You probably wouldn't look at the density when you're considering materials, but there's a very interesting column on density. You can see, again, the synthetic materials, similar-ish, the fibrous materials, the wool type products, similar-ish, until you start getting into boards, straw, cork, into hemcrete, you're really sort of beginning to ramp up the density. Now on my screen, I've got everyone there. I'm going to move that over. I don't know if you can see this column. Anyway, then you've got the specific heat capacity, which I'm pretty sure no one will ever look at when they're considering insulation. But generally, plant-based materials tend to have quite a high specific heat capacity, second only to water generally. The plastics are sort of mid-range, and then the synthetic fibers much lower again. Anyway, sorry, I am going to be, as I say, a bit heavy on the tables. So hopefully to explain this, I'm going to use a few different scenarios because I couldn't think of any other way of doing it. So if we look at a house then that is designed for a busy working couple, or busy working people that spend a lot of time away, they might only come back a few evenings a week. They might be around one day at the weekend. They might just sleep there overnight. They're really not occupying the building for very long. So again, going back to our wonderful table. So we've got the properties we were looking at before there, and if we look at the thicknesses of all the various different insulation materials, you can get a bit more of a comparator, but typically, again, the walls are sort of 75 mil, mainly because you've got to put them between battens. The boards about 60 mil. So this is all to get a U value of less than 0.5, which is what Mark and Martin have been talking about. Again, all fairly similar values except for hemcrete, which is, again, pretty uncommon internal wall insulation, but I thought I'd put it in there for interest. Up at 110, whereas PIR, when you're using insulation back plasterboard, typically you'd be using a 40 mil layer on the back of your plasterboard. Now, if you only live in a house intermittently, you're only going to be turning on the heating for short periods of time when you come back. So you don't necessarily want a building that is going to take ages and ages to heat up. So if you come back, say, it's relatively cold, certainly in the cooler months of the year, it might only be 15, 16 degrees inside. You want to warm it up. You want to get it up to sort of 21, 22 degrees. Now, just the insulation materials in the walls do actually soak up quite a bit of heat energy. And this column here is looking at how much energy those materials are soaking up. So the synthetic materials down the bottom here are soaking up very, very little. Hemcrete is soaking up quite an enormous amount. Wood fiber, fairly substantial amount, and then the others are, again, relatively similar. And then to sort of put a metric on that, I've related that back to the output out of your underfloor heating system. To really show what impact that's having on the way that the building warms up. So you can see that really heavy materials like hemcrete and wood fiber are really soaking up huge amounts of energy before their temperature is actually reaching equilibrium with the internal temperatures. In the case of hemcrete, you're looking at well over half an hour. Wood fiber is about sort of 17 minutes. Typically, I'm hoping that people wouldn't be using these kind of insulation materials for all the reasons that Martin's been describing, but certainly looking at the natural fiber materials, you would probably consider using sheep's wool, possibly hemp wool, to insulate the inside of those walls so that the walls aren't putting an additional burden on the heating system to actually warm the building up. So using these kind of lightweight materials creates a building that quite quickly changes temperature. So This is an example really where you actually don't want a lot of thermal mass. You've got infrequent occupation, you've got a lot of probably a lot more use during the winter months. You do want that lightweight building and lower thermal mass so that you flick the heating on and quite quickly you're up to temperature. If you did use higher mass materials, basically you'd be having to leave the heating on for a longer period of time to actually warm the building up. The occupants probably would have left the building by the time that all of that heat is then dissipated from the material, and so effectively you're kind of wasting that heat. So that's the first example where actually a high thermal mass isn't necessarily useful. We're going to use much the same properties again now, but in a slightly different occupancy style. So if you've got an internally insulated house, it's got quite a bit of southerly glazing. We're looking more at spring and autumn time, where you've got a lot of solar gain through the windows. The sun is strong. Shading doesn't do anything because the sun's still quite low. So you get quite a lot of heat gain through those windows. The occupants are living there, probably a more common lifestyle where you're in every evening and morning. You might be around for some parts of the day, but you're generally at home most of the time. So again, we've got all our properties, we've got our thicknesses there. Again, looking at those, this column here with the amount of energy that the materials are soaking up. Now we're looking at it with a different lens this time, really, because the heat, instead of being provided by the underfloor heating system, is actually provided by the heat from the sun. The sun's piling in through the windows. And actually, for quite a substantial amount of the day, you've got a lot of heat gain through your windows. So again, if your overnight temperature in the house might drop down to 15, 16 degrees, just to heat it up to 21 degrees, this is the amount of energy that you'd be absorbing. So again, the walls are sucking heat out of the internal environment and actually keeping that nice, stable internal environment that you're looking for. Now, the other property that I mentioned at the beginning is thermal effusivity. And this is, as I say, the rate at which these materials transfer heat back. So, I mean, looking at wood fiber, because it's one that we work with a lot, it's absorbing quite a lot of heat energy. It's also releasing quite a lot of heat energy back into the room once the solar gain has stopped. And so the benefit of that, and again, you can see the much the same diagram there as the energy storage per square meter. These higher mass materials are soaking up heat out of the room and keeping that nice stable temperature. So with this kind of occupation, you really would benefit from having high thermal mass linings, particularly in the spring and autumn. You need something to attenuate those solar gains, because otherwise the building gets very hot. And again, if you're there during the day, or if you come back at the end of the day and the building's hot, more than likely you're just going to open the doors and windows and dump that heat outside if it isn't soaked up by the building itself. If those heat gains are soaked up during the day, you come back to a nice, warm, comfortable building. Those heat gains are slowly radiated back towards the interior, and that pushes the time at which you might start putting your heating on much further back. And again, having materials that with high effusivity, higher ability to transfer that heat back, also means that again you're radiating more of the heat rather than not. So and then really the final scenario is looking at more summertime temperatures. So looking at brick buildings, particularly, as Mark said, there is a huge variation in the density of brick and the thermal conductivity, particularly up around Manchester, Blackburn, those kind of areas. There's a lot of really hard, dense brick, which is used to build buildings, and they really do have a conductivity at sort of 0.8, 0.9. Whereas the old historic bricks, London stock bricks, for example, go down right the way down to sort of 0.4. So in the more extreme examples, if you've got these buildings with relatively high conductivity bricks, there's no overhang on the walls. The walls are soaking up heat all through the day. And we're talking about the middle of summer here. So you've got, quite commonly, as I said, you've got daytime temperatures up to 30 degrees. and the air temperatures are peaking at about 4 o'clock in the afternoon. The solar gain of the wall is probably going to be peaking around about 2-ish, but it also takes a couple of hours for that heat to transfer through into the room. So around about 4 o'clock, an uninsulated wall, not only have you got high air temperatures, but you've also got heat radiating inwards from your masonry. So again, back to the table. This time we're going to be looking at thermal diffusivity. So this is the speed at which heat moves through those materials and into the room inside. So the lower the number here, the longer it takes. Again, you've got the fibers up here, sort of 2, 4, 6, that kind of range. Wood fiber down at 1.13. Hempcrete, even though it's very, very dense and very thermally, no, sorry, that's cool. Where are we? Hempcrete down here, 1.68. Even though the hempcrete is very, very dense and very thermally massive, actually the diffusivity is a little bit higher than it would be with a typical wood fiber board. Looking at your synthetic materials, they've got really very, very high diffusivity. So heat absolutely flies through them, particularly expanded polystyrene. So if we then turn that into something that's hopefully a bit more meaningful, and that's the time taken for those heat changes to penetrate through into the room. Now, looking at, again, these synthetic materials down here, so you've got heat radiating from your brickwork, it's coming into the room. These materials are only going to offer, well, anything between 6 and 20-minute delays to that heat radiating into the room. With wood fiber, you've got 2 and 2.25 hours. With hempcrete, you've got the best part of 5 hours. But looking at that, again, looking at the time taken, essentially what we're doing here is you've got heat radiating out from your masonry. The longer you can delay that radiation from the masonry, the more likely you are to be able to bring cooler air from outside into the room and make the room a lot more comfortable. Now, if you're elderly, if you're disabled, if you're at home a lot and your health is impaired for any reason, in the middle of summer, we already around about 2,000 people are dying each year just from overheating, and that was before we sort of had this spate of heat waves that we've recently had. So those figures are going to go up and up, and unless we look at ways to passively mitigate that, then obviously more and more people are going to succumb to that. So that decrement delay, which is what it's called, the sort of shifting of phase, helps stabilize the internal temperatures, allows you to use cooler external air to be drawn in, and really reduces your reliance even on things like air conditioning to keep the building cool. So those are 3 different examples, really just showing how the different products work. But okay, there are certain instances where the lighter weight materials really are beneficial, but equally, depending on what the need of your customer is, then you might also want to look at the heavier weight materials to make the internal environment more stable and more comfortable. I think that was it. I'm bang on time-wise.